full energy today.
Yeah.
Right? It's very have a long weekend rest after the long weekend, right? So more January. The weekend.
No, my weekend is not something special. I just therefore I sleep all day.
Alright, so let's start the lectures. Ready? Alright. So the previous class, we stopped here, right? So who already finished this? Very good. So did you do this one? Not yet? Forgot? So now I spend some minutes and then we do this together, okay? This exercise is an example of projectile motion. And with the projectile motion, initially, you, let's say, inject an object, for example, particles, at this point, with the initial velocity v0 vectors, making an arrow to the horizontal axis is theta. So for example, I choose this axis OX, this OY. So in this case, you need two components to describe the motion of this particle. One dimension is not enough. In this case, you need two dimensions. Okay? Because the object will be moving in a plane instead of a straight line. Alright? So with the initial velocity v0, you can resolve along OX. So you have v0x components is equal to v0 cosine theta, and v0 along y components you have v0 sine theta. Okay? So you project the object up and let it free, and you forget air resistance and all the other force acting on the object except gravitational force. Okay? So in this case, here we have the acceleration of the object is equal to acceleration of the object equal to g, right? Gravitational acceleration, free fall motion, free fall acceleration. Because you just have gravitational force acting on the objects. So A equal to g, and then g is vertically downwards. This is a vector g. Alright. So tell me, in this case, if I resolve along OX and OY, how about the x component of the acceleration equal to? Very good, 0. Acceleration along OY equal to?
G.
Who, please?
It's minus G.
Very good, y minus? Y minus.
Because the object is falling down to the negative of
No,
y.
no, the object is not falling down. Please project up. No, no, not free fall motion. It's I project up and it's moving like this.
Ah, yeah, like this.
Yeah, right. Like this.
Cái này nó theo cái trừ g dẫn tốc theo g vì là cái vật này nó chỉ tắt cái lưỡi của trái đất.
Okay. So because G is pointing vertically downwards, and you are choosing OY is going up.
Yeah.
Okay? OY is going up, and G is going down. That is why you have the components of the acceleration along OY is minus G. But in case some of you can choose the direction is downward. So then in this case is plus G. So plus or minus, depending on the direction of the positive direction or y. Okay? In this case, it's completely correct. AY minus G. So you have this information. You can calculate the velocity along OX at the time t. Okay? Equal to V0x plus AX t. And Vy at the time t equal to V0y plus AY t. Okay? And then you just plug in the value you already calculate of this step and this step. So, then I have Vx at the time t equal to V0 cos theta. Ax is 0. Vy at the time t equal to V0 sin theta minus G. Okay. How about the position x and y? x0. x0 is 0. Plus V0 xt is this one. V0 cos theta t plus xt square over 2, t square over 2 here, but it's 0. So I have y equal to V0 sin theta t minus gt square over 2. Okay? So you see that the velocity along y is constant. Doesn't depend on t. Doesn't depend on time. So it's always constant. And the velocity along y is depending on time's linear function. V0 sin theta, it's a linear function, right? The time. Okay. So now find the horizontal range. Horizontal range is you start here and you are traveling at these trajectories and then you're falling down this. So for example here is the ground. So the horizontal range is you measure the distance from the starting point to the end points, the horizontal length. So the length along the horizontal axis. The name is horizontal range. Okay? So R is equal to X at these times. So how can you calculate this? So at this point, I denote this the point M at the point M. So actually, R is equal to X at the M, right? How can you maximize R now? Who can suggest? Hmm? Yeah.
Không phải định nghĩa gì ạ?
How to find? Tell me how to find the horizontal length. Horizontal length when you reach the egg, right? And then you calculate the distance. The distance from here to here.
Find the x.
How can you calculate? Yeah, find x. So how can you find x?
Ngày xưa em chơi đã hiểu tiếng Việt hơn không? Sáng nay em sao? Đương nhiên là không có. Chịu, sáng nay máu chơi não chưa lốp được. Dạ, tiếng Việt được không? Tiếng Anh không? Okay, so about the distance between O and M can be calculated by V multiple T.
V multiple t. Alright, V0x multiply t. Okay, but how can you calculate the t? The time. Right? You need the time. You determine the distance. How can you get this information?
T.
You look at the. So what do you think at M you have which information?
We have
Can you get the position along Y at M? Y at M equal to what? So when you're standing here, what is the position along Y?
Bạn ấy thì y bằng không.
Right, very good. So based on this, you can get the information for the time t.
Yeah.
Okay, right. Thank you very much. Excellent. So he said that at this point, the position along Y is 0. So you have Y at M equal to 0. And then you plug to here. Then you have V0 sine theta multiplied by T at M, right? Minus GT at Rm square over 2 equal to 0. Alright? So, can you solve this equation? Give you two solutions. You have the first solution is Tm equal to 0, right? And Tm equal to so it's I don't have enough space. 2v0 sine theta divided by g. Okay? So Tm equal to 0 is corresponding to which time? This time. Okay? So we have two instants at there with the displacement along y0, that is the initial position, and this one. So this solution equal to T0, equal to 0. And then Tm equal to this is at this times. So from here you plug to here to get the x at M is V0 cosine theta multiplied by T at M, and T at M is here. So the information is V0 cos theta to V0 sine theta divided by G. And then the result is, you get this result. for the horizontal rays. Okay? Clear? This is where you get the horizontal rays. And then from this formula, you see that if V0 is constant, G is constant. You change the angle. Right? So you see that the horizontal rays will be depending on the angle. And then it get the maximum value when the sine 2 theta is 1. And that is angle 45 degree. So if you project with the 45 degree, you will get these horizontal rays. Okay? So this is the way how can you catch this the target, because you can measure the horizontal rays. Okay? So the amplitude, now you calculate this one at this point. So this point I denote is n. How can you calculate the amplitude with information you have? Who can suggest me the way to determine
in the end point, the V is equal to the V, Y equal to
V, but the V is horizontal because it's a tangent. And Vy is equal to? Very good. And then you base on this to calculate the time. I see. Yeah, very good. So let's say that at this point, the vector velocity is a tangent to the trajectory. Okay? So tangent here is the highest position. So the velocity is pointing this direction, V. And then if he resolve V along y, because it's perpendicular, it's parallel to the horizontal, means perpendicular to the y, and so from here he can get the Vn along y equal to 0. And then he plug to this formula, Vy here. So from here he get what? V0 sine theta minus g Tn equal to 0. And from here he can calculate, it's a small space, the times to get n equal to V0 sine theta divided by g. And n is y at n, right? Look.
Yes.
Very good. So amplitude equal to the y components at n. So you have this equation for to determine y here. So equal to V0 sine theta multiplied by t and n minus g t and n squared over 2, and then you have Tn at this formula. Let me see. I don't know why it's so thick. Oh. Is it clear to you? Yeah. I can get more space. So you plug Tn here. Okay. Tn is you get from here, and then this the results. You plug the results in, and then you get the results is V0 squared over 2 here. So the result is here. It's different. Okay. I have no choice. So it is V0 squared sine squared theta divided by 2g. And here again you see the amplitude depending on the angle. And you get the maximum value when sine squared theta is equal to 1, and the maximum when theta equal to pi over 2. So this direction. If you project this direction, you will have highest position, highest amplitude. And the highest amplitude is this, V0 squared divided by 2g. Okay? With this angle. Any question? Clear? So here, this all step for you to solve the exercise with the projectile motion. And I already give you the list of the exercise. Maybe you already during tutor. Okay? Now we move to this part. Relative motion. Relative motion is from the first class when we learn about the motion. I already told you that motion is relative. So you can move with respect to this object, but you doesn't move with respect to another object. Okay? So we already I already gave you a lot of example. For example, we are sitting on the train and the train is moving. So we are rest with respect to the train, or someone is sitting on the train. But you are moving with respect to the someone standing on the ground. Alright? So depend on the frame, reference frame. So let's say if you are considering the object is a frame number 1, and then the frame 2, and then you have frame 3. Okay. So, for example, this one is you. This one is the train. And this one is the ground, for example. So I will have the V12 is the velocity of the object with respect to the frame 2, that is the train. And V23 is velocity of the frame 2, so velocity of the train with respect to the ground. 2, 3. And then the way you get the velocity of the object 1 with respect to the frame 3 is you use the adding rule in the rule of the adding vectors. V13 equal to V12 plus V23. For example, you have V12 is pointing along this direction. This is V12. And then V23 along this direction. So then, the velocity of the object 1 with respect to the frame 3 is this vector, V13. Okay? It is the way. And then you have the exercise on the list of the side are behind this. And similarly, for the displacement, you get the same. The displacement of the object 1 with respect to the frame 3 equal to the position or the displacement of the object 1 with respect to the frame 2 plus position of frame 2 with respect to 3. Exactly the same. And also relative acceleration, we have the same rule. And then the same rule of the acting vector as I show for the velocity. Is it clear? And did you do the exercise related to this? Yes? Did you have the tutor? Yeah. Not yet. Okay. So do the exercise and you correct during the tutor. So today we move to the new chapter. Chapter 2, we will learn about the force and the Newton's law of motion. So this chapter, we will learn about the dynamics of the object. So we will learn why the object can move or why the object cannot move. The reason of the motion to cause the motion of objects. So first of all, I will introduce about the force. Okay? So what is the force? The force is something to push. Okay? To push or to pull. This the force. So you can push the person beside you. You push here or you pull. So that is the force. And the force is a vector quantity. The vector quantity means it has the length, the magnitude, and the direction. If you push, the direction is go to the left, right? If I pull, so the direction is going to the right. That is the direction. And the unit of force is the Newton. Get the name of the scientist, Isaac Newton. And in the general case, an object can be acted by many types of force at the same time. Okay? For example, I'm standing here. There is a force, is a gravitational force. And the normal reactions of the floor on my body. I will introduce you the everyday life, the force in the everyday life later. So the next point, you will see the balance force. The balance force. What is the balance force? So when an object, I'm standing here, I am acting by many force, like the gravitational force and the force, normal force acts by the ground on my body, and maybe other force. Yeah, the weight is a gravitational force. Okay? And I am at rest, in equilibrium. So in this case, I say that I am acted by many force, but the resultant of the action is zero. The resultant of the action means I make the vector sum of all the force acting on my body. Okay? So I can say the resultant force resultant external force. External force means the force outside of my body, right? I denote is the resultant or the total resultant force is the vector sum of all the force acting on my body. If it's balanced, you get 0. If all the force, vector sum, remember, vector sum is 0, means the total force or resultant force acting on the body is 0, and then you said that F1, F2, F3, and it's balanced, they are balanced. And then in this case, no external force acting on the body. If the motion of a given body is not disturbed by the external influence, so in this case, in case of the balanced force, you say that the motion is not disturbed by the external influence. Then the body will move with the constant velocity. So if I am resting, I will be at rest forever. If I am moving, I will move with the constant velocity. Okay? That is the contents of the first law of Newton. And then we already know from the previous chapter that in case of motion with the constant velocity, how about the trajectory? A curve or straight line? Straight line. Very good. Straight line. That is a straight line and then obeys this formula. The position at the time t r equal to r0 plus vt. So this you know already in the vector form, because we are considering the general case the motion in 3 dimensions. If v is not 0, so means that the object is moving, the object continues to move in the straight line with a constant speed. And if v 0, it will be at rest forever. So this in case of the balanced force, and that is the content of the first law of Newton. So what is the meanings of the first law of Newton? It looks easy, but then it's very, very important. So remember, he said that when the force acting on the object is 0, balance, then the object will move with a constant velocity. Vice versa, if the object is not moving with a constant velocity changes. It means there will be some external force acting on the object, but the resultant force acting on the object is not 0 anymore. There's some additional external force acting on the object. Okay? For example, I am resting, and all the force acting on my body are balanced. Now I'm moving and someone else push me. I'm moving. So in this case, I change the velocity. And from this law, you can confirm that. Obviously, I am acted by some external force. Okay? And also another meaning is the laws of Newton. Is correct only is called the initial frame. Inertial frame. Inertial frame is the frame in that case the laws of Newton is correct. So you will learn the inertial frame. Is the laws of Newton is correct? That means, he said that in this frame, if all the force acting on my body are balanced, I will be at rest or moving with a constant velocity. If that is not true, if you show that all the external force acting on my body is zero, but I change the velocity. So you can conclude that in this case, the laws of Newton is not correct anymore. And then your frame, the frame is not inertial anymore. Okay? So the inertial frame, what is the inertial frame? The inertial frame is a frame. In that frame, the law of Newton is correct. So you can test. You can test the frame of the floor is an inertial frame or not.
It's an inertial frame.
Yeah, because you put some object resting on the floor, and then you don't touch any other force here, and then it's at rest, right?
Yeah.
So in this case, you have gravitational force is balanced to the normal contact force, and they are balanced, and then your bottle is at rest. Yeah. Good. I make another example. I have the microphones. It's a similar to it, right?
Yes.
It's at rest. So the frame of the table is inertial frame. So now, I don't touch to the microphone, right?
Yes.
I don't do anything. I just stop the metal. I make this. It's moving. Do you see?
Yeah, I see this.
So what does it mean? I didn't touch the microphone, right? My hand is another place. And then in this case, I don't touch it, and no one touch it. So the force acting on the object is still balanced, right? Agree? But the object moved. Change the velocity from rest to move. So this law is not correct anymore. So it means that you said in this case, the frame of the table is not inertial anymore because it's moving with respect to the ground. Okay? So you can say the ground is the inertial frame, but with some other frame moving with respect to the ground, with some acceleration, then that frame is not inertial anymore. And then in this case, on this frame, the laws of Newton is not correct anymore. So what is we state here is not correct anymore. Okay? Because the frame is not inertial anymore. Not the law is not correct, but the frame is not inertial anymore. Because the condition to apply this law is the frame needs to be inertial. Is it clear to you?
Yes.
Okay. So that is, who can give me another example? You are resting, and then the frame is moving, and then you are moving. The train or the car. At the beginning, they are resting with you, with respect to rounds.
Yes.
And then the car, or you are sitting on the motorbike, okay?
Yes.
And then you increase the velocity. And then the people sitting on the car is acting on this. Agree?
Yes.
So, you change the velocity
Becomes change.
because the frame on of the motorbike or the car is not inertial anymore. And now this rule is not correct anymore. And then we go to the next slide to see in this case why we can move like this. Or the minor bodies can move. Why is that? Why? How to explain? In the case we have the frame, not inertial frame. What happened in this frame? How we can analyze the force acting on the object. Okay? So, let's start. Unbalanced force. So still, now we go back with the inertial frame. Okay? I will go. We will come back with the non-inertial frame later. But now we deal with the inertial frame. So in the inertial frame, the case of unbalanced force acting on the object. So if unbalanced force acting on the object, if the resultant force is not zero, okay? So you sum all the force at 1, at 2, at 3, at n, but the sum is not zero. So in this case, you say that non-balanced force acting on the object. Okay? So all the unbalanced force can change when you are acting with the unbalanced force. So the unbalanced force can change the motions of an object, and it can cause a stationary object to move. Okay? Firstly, I'm stationary, and then if I'm act by the external force, someone push me. So in this case, the total force acting on my body is not balanced anymore, and I'm moving. Okay? So it causes a stationary object to move. Second, the speed of the object to increase. Maybe you are moving constant, and then maybe to increase if you have more force acting on the body, right? And the third point can be decreased. So I'm moving very fast. Now I brake, and then go slowly. Okay? So of course in this case you need to add some force to resist to decrease the speed. Okay? Or another case, if you were to change the direction of motion. So I'm moving this direction, now I want to turn. So it needs some force. So someone hit me at this direction and then I'm moving. I change the direction. So change the direction of the motion, increase the speed, decrease the speed. Then you say that obviously unbalanced force already acting on the object. Vice versa, if you are acted by unbalanced force, then your speed will change, increase, regress, or change the direction. Alright, so that is the second law of Newton. And how is it changed? We go to the second law of the motion of the Newton law. So firstly, I introduce the quantity equal momentums of objects. So I have an object with a mass m. Mass m is moving on the road with the velocity v, vector v. So the momentums I denote at the vector p equal to the multiplication of m multiplied by v. M is the mass of the objects. V is the vector velocity. So you see that the momentums and velocity, they are pointing along the same directions, and then that is the direction of motion. Okay? And the magnitude of the momentums you multiply by the mass. And the dimension is kilogram meter per second. Okay? This is the dimension of the momentums. The second law of Newton said that when you have the net influence force acting on the objects, so this is a resultant force acting on the object, total force. Total force. So I mean F total vector equal to F1 vector sum of all the force acting on the objects. Okay? So this guy, I denote as F, is equal to the change of the momentums with respect to times. So I'm acting some force on the objects during some time, period delta t. And during this period, under the influence, it changes the velocity. And the velocity makes the changing of the momentums. And how much the momentum changes per unit of times, giving you the net of the force. Okay? For example, so the formula is delta P over delta T. So for example, if you act on the object's 1 Newton force, you can change delta P during 1 second. So in this case, the delta P is changing 1 kilogram meter per second. So for example, if initially P0 equal to 0, velocity is 0, so then delta P equal to 1 means the P equal to 1 kilogram meter per second or 1 Newton meter. So the dimension of this, you see, momentum equal to force multiplied by times. So the unit is a Newton meter, also the unit of the momentums. So when you are act by the force 1 Newton, you change the momentums 1 Newton meter per second. Okay? For each second, this force change the momentum to 1, and then if you acting more times, 1 second more, so the momentum increase to 2 Newton meter, increase to 3, to 4. Every second, it increase the momentum 1 Newton meter. That is the meaning. Okay? So the force, it can measure how much you change the momentums per unit of time. Is clear? And vice versa, if you want to calculate, if you know the changing of the momentums, you divide by the times acting of the force, and then you can calculate the average value of the force acting on the objects. That is the meaning of the force. Okay? So before maybe you know, okay, the force acting on the object, but how can you quantify the big force and the small force? So we said that the force big if that is the rate of the change of the momentum, right?
Yes.
If you change the momentum fast,
The force is big.
big, and then if you change the momentum slowly,
The force is small.
right? And momentum is related to velocity. So if you change the velocity fast, so mean which quantity we think about when you change the velocity, because the mass doesn't change. So when you change the momentum, means you change the speed or the velocity. So the velocity changes fast. So which quantity is it?
Acceleration.
Acceleration. Very good. So force is proportional to acceleration. If the force is big, acceleration is big, and vice versa. So force is small, the acceleration is small. And then the force is zero. Acceleration is zero, and then you don't change the momentum. And then you don't change the velocity. And then the force are balanced. No force. No net force acting on the object. Okay? Is it clear? So, that is the average value of the force. And now if you consider the time is very, very small, then the t is very, very small. Then you get the derivative. Okay? dp by dt equal to f. So here the instantaneous value of the force is the first derivative of the momentum with respect to time. So this way is maybe new for you. Okay? So from high school, you know this one. When the mass of the object is constant, then you plug to here, P equal to mv, so F equal to d of mv by dt. So m is constant with respect to time, you can get it out, m dv by dt. So dv by dt is acceleration, very good. So you get this form, you go back, this form of the second law of Newton which you have learned from high school. But originally, remember, originally Newton have this form. The change of the momentum. This is more general because this still corrects for the mass, for the object change the mass with time. So who can give me some example? You see there are some object changing the mass with time. You also change the mass with time, right?
Yes.
Before eating and after eating, okay? For example, okay? But you need to like the that change, but in fact it changes. Okay? Some other example. And other example, you can see it change the mass. If the motorbike on the car is moving, if the mass, total mass of the car is the car plus the mass of the flow of oil or petrol, okay? So then if you go, the petrol in the car is decrease.
Yes.
So then the total mass decrease. Right? And many other cases. And then for the some of you heard about the problem is some atomic they are decaying to another one. So during this time, the mass changes. So in fact, in the reality, we always consider the mass of the object doesn't change because you consider the motion in a very short time. It's not big enough. But it's very long, so it changes the mass. So in the short time, maybe you consider the mass doesn't change. Okay? That is the second law of Newton. So far you know is the rate of the change of momentum of object is directly proportional to the applied force, and it also along the direction of the force. So you get this formula. F d by dt of mv Okay. So now you make the integration in both sides from T1 to T2 of F dt, and then you will get the changing of the momentum, this delta P. The final momentums, so you are moving at the times T1 here, T2 you are here. At the time T1 the velocity is u, T2 is the velocity v. So the changing of the momentum is mv minus mu equal to integration of f dt. Okay? So you said that this quantity is called the impulse of the force. Impulse of the force F equal to the change in the momentums. Okay? Impulse of the force. So in case if the force is constant, you get this graph. The force and these are times. If the force is a constant with time, for which line you have? Horizontal line. From T1 to T2. The force is a horizontal. It doesn't change with time. Okay? So the integration of f dt is the constant multiplied by the delta t, so is it the area of this? Okay? Area. So this area is impulse of the constant force. This T1 here, T2 here. So delta t, this one is F. So F multiplied by the times duration. So you see this integration of this part. So you more summarize, generalize this case. For example, you have the force, and depending on the times, it's not constant anymore. So like this. So in this case, the impulse of the force from T1 here, T2 here. The changing of the momentums between T1 and T2 is area of the graph, area below the graph F and T. Okay? Here, give you the delta P. Alright? It's similarly as before, you get the velocity time graph, and then you get the distance. For example, you do this exercise. To calculate this exercise, give me the results. Uh, 2 minutes. Hello, you finish? The result is 17. 1, 7, 17. Right? 17. 7, 0. Other results? It's okay? Let's check. So let's check together. Alors, so it's better than the force F. So the F is changed with time. It's not constant, but change with this function. Increase in momentums of the object after 8 seconds. 8 seconds here. 0 here. So the changing in the momentum is equal to any of this below the ft graph. So this error equal to 1/2 of this plus this multiplied by this. Agree?
Yes.
So this one equal to what? 6. 6 plus 8 multiplied by?
Teacher, 8 is not 7.
No, this 10.
But that's not 7, it's 8.
Sorry. Thank you. I confused. 8. Thank you. So this one equal to 70. What is the unit? Kilogram meter per second. Very good. Or? Very good. Very easy, right? So from this graph, so this guy is for the impulse of the force during this time. Another example. To apply the second law of Newton. In this case, you apply the second law of Newton of the form F total acting on the object equal to the mass multiplied by acceleration of the object. So you regulate the changing of the mass with time. Okay? Number A, B, and C. Three cases. So I will call two persons to the board to do the B and C. And the first one we do together. Okay? The train accelerates uniformly. The train moves with the uniform velocity. The train retards uniformly. Hello? Finish? Who can do the first one? Right? Or I correct the first one and then someone do the second one. Or I call one person go to A and one person go to C. Who number 8? Some new points. I need some new points. A. Today I didn't get any new name. Already the name I know already. That's the name I know already. Then some new name, new face today. A. Who can do A? Hai bạn này cô thuộc mặt quá rồi này. Ai ở sau là sao nhỉ? Cái bạn kia kìa. Bạn kia bạn gì nhỉ? Bạn Giang hay bạn gì nhỉ? Hoàng Minh à? Hoàng Minh. Đâu? Ấy. No one know? This is not correct, no problem.
Quay
A. Yeah, you. Yes. Your name? Bạn ấy cũng không phải là bạn mới, cô nghĩ là cô biết tên bạn là cô quên mất rồi. Ok, tên bạn là number C. Con làm câu nào? Câu A. Ok, con làm câu A. Nhưng bạn này nữa là câu C đúng không? Con làm câu nào? Câu nào cũng được, very good. Wow. Câu nào cũng được. Câu C.
My name is Vinh.
Vinh Quang. Vinh câu A, Quang câu C. Ok? Xem có phải không? Nói ai? Tên là gì Vinh nhỉ? Bà Vinh này. Cái gì Quang nhỉ? Bởi vì lớp có mấy bạn Quang liền. Hồng Quang.
Lê Hồng Quang.
Bà Vinh Hồng Quang.
Lê Hồng Quang.
Lucas.
Không biết thầy chú lại trở lại.
Maybe difficult for you to look at this, so I will translate later. So the other you check answer. If not correct, then you have a chance to correct it. Bài làm đâu? hiểu như thế nào thì tiếp theo của nó sẽ là như thế nào. Đó. Như tự nhiên đấy. There's some question. You have more input. Okay? Đây câu hỏi người ta cho thừa dữ kiện. Problem 1 to 2. Accelerate. Accelerate and wing setup is go to the right. Right, wing? Go to the right. Is it correct or not? No? No? Who say no? Đức? Yeah? What's your name? Here, new face. Can you introduce? Khôi, okay. Khôi, you said that is not correct, right? Can you explain? The train is accelerate uniformly. So firstly is stationary. And all the train is stationary. But if you look at the mark is on the ground, okay? And the train is here. So when the train is moving, accelerate. What is the position of the ball with respect to the mark? Okay, that is the question. Go to the right of the mark or go to the left of the mark? Because the mark is on the ground. Go to the right. So, Bhavin, you have the opposite direction with Bhavin. Wing setup is go to the right. Which leads to the mark is here. And it's go to the right of the mark. Is it okay? Uniform acceleration. F equal to ma. But where is F1? The quantum. Okay. You think about the quantum and how long you got that? Rồi. Okay. Rồi. Cân bằng mỗi lượt cân lên. Okay. Alright. But be careful with the way you determine the force, inertial force. Okay, Hồng Quang. Okay, thank you, Vinh. Alright, so we correct together. So the results of Vinh is go to the right. A. Number C. Quang go to the left. Is okay? Okay, thank you. Thank you. Okay. So Quang go to the number C, go to the left. Number A, go to the right. So now we deal with the case A. Go to the right. Who agree with Vinh? Who agree with Vinh? No one? Vinh. No one agree with you. So who said is go to the left? Look. Khôi. Yeah. And I forgot your name. Bạn nữ tên gì nhỉ? Con tên ở đây. Yes. Ah. Right, that is a good question. It's from the roof of the train carriage. The bob is particularly about the mark when the train is stationary. Draw the figure, show the position of the mark when the train accelerates uniformly. So you have to assume the direction of the train for each case. Exactly. So, very good question. So, which direction of motion of the train in this case?
Move to the left.
Ah, you are moving to the left. All right. And Quang?
Left.
Go to the right or the left? The direction of motion. Go to the right. Yeah. Thì có hỏi tên bạn nữa đấy. Tên gì đấy? Tôi gọi bạn là vẽ phát không nghe. Toàn đây bạn Nam là. Con tên gì nhỉ? Châu. Gì Châu? Nguyễn Châu. Minh Châu. Thank you. Rồi, thêm một bạn nữa xuất hiện. Minh Châu. So, thank you Đức very much. So now it's very important that we need to assume which direction of the motion of the train. So, Vinh said that he assumed the train go to the left. And in this case, the bob is go to the right. Is it okay or not? Okay, okay. So now we are correct, Vinh. Okay, thank you very much. And in the case, Quang, number C, Quang said that the train go to the right, and the bob also go to the right.
The left.
No, go to the left. Go to the left in the case of the decelerate. Is it correct or not?
Not correct.
It's not correct. So what do you think?
I think because the train now is accelerated, so the direction of moving is opposite to the direction of the force.
Acceleration.
Yeah. So I think in this case, this train should move to the left, so it will be correct.
Okay. If you assume the train go to the left, then the bob also go to the left. Okay. Alright. Thank you very much. Quang also very good. So he has some idea, but I will explain why is that. Okay. Thank you very much.
Đeo quang, đeo quang.
So happy. Alright, so now we will do this together, explain why. And Vinh and Quang told me that they deal with some initial force. Lực quản tính, initial force, inertia force. They introduce something called inertial force. So in this case, I will instantly write what is inertial force. Now we go back with the example I drew previously. So Lum
Yes.
already showed the example. He put the bottle on the floor, and then the bottle is at rest forever, and then in this case all the force acting on the bottle is balanced.
Yes.
So now on the Suga, you are sitting on the car, and the car is accelerate. So what do you do?
I will.
And the bottle is maybe falling down, or is moving, right? It's not at rest anymore. So in this case, the frame. So the first law of Newton said that when the net force acting on the object is zero, it should stay at rest forever or moving with a constant velocity. In case of inertial frame, now, still the force acting on the bottle is the same because you didn't touch any force on the bottle, right? But the only difference is the frame is moving. So, and the bottle is moving. So in this case, you cannot say the first law of Newton is not correct, but the frame is not inertial anymore. And in the frame is not inertial. There is additional force acting on the object. That is called inertial force. And the definition for the inertial frame. You have the ground is the inertial frame. And the other frame is moving with some acceleration with respect to the ground. It's not inertial frame. If the frame moving with a constant velocity with respect to ground, so this frame is still inertial. Okay? So, first, we need to define the initial frame. So we have the grounds, it's the inertial frame. So you have another frame is the car or the train, it's a moving. If the frame of the train, on the train, if the train is moving constantly, velocity, then the frame of the train is inertial. If V changes, then the frame of the train is not inertial anymore. And in this case, the new force appears if you considering the motion in this frame. That is the inertial force. So inertial force equal to minus the mass of the objects multiplied by acceleration of the frame. Okay? So moving change giving the acceleration of the frame, the acceleration of the train with respect to the ground. And then if you consider a mass on the train, so it will be acted by the initial force, that is the opposite minus side, opposite direction with the acceleration of the frame multiplied by the mass. Here is the co-initial force. So with the initial force, we can explain the case when Lum sitting on the motorbike. And initially the motorbike is at rest. And now he increased the velocity. And he said that he is like this. Because the car is moving and the accelerate. So the acceleration of the motorbike is go to the right. So in this case, the initial force is opposite to the acceleration, act backwards. So making his body like this. Okay? Another case, if he's moving and then he stops. case, deceleration. Deceleration, so the direction of the acceleration is opposite to the direction of motion. Okay? And then the inertial force is opposite to the acceleration, so his body is acting to the forward direction. Do you agree?
Okay.
Okay, so that is the inertial force. And then now we will deal with this case. So in this case, it is very, very important to assume the direction of motion. So that we know the direction of the acceleration. Otherwise, we don't know, right? So we assume that, like Wing is doing, we assume that this is a train and the map is the ground, right? So this guy is the inertial frame, and the train is not inertial. It's an inertial frame. So we assume that the direction of motion of the train is go to the left. So in this case, number A, if the train go to the left and then he is accelerate, then the acceleration of the train is the same direction as the velocity in case of acceleration. So you have A. In C, this direction. So because A is like this, so the force acting, so initially you have the weight, gravitational force and the tension. They are balanced at the beginning. But when the train is moving with the acceleration AC, then it will back by the inertial force, making the ball moving to the right. It's moved to the right until new position. And because accelerate uniformly means the magnitude of AC is constant. So you analyze the force acting on the object is mg, this T, and this inertial force. Because this guy is constant, this is constant. And then at this point, the bob is at rest on the train at this position, theta. And satisfy on the train, you have T plus equal to 0. And then they are balanced, and then this address. But balanced with the new appearance of the inertial force, making the ball moving to the right. Okay? And number B, when moving with the uniform velocity, how about the acceleration? 0, right? And then is it have the inertial force or not? No. So it's still here. Still here, number B. C. A. A0. Number C, the train go down uniformly. So it's go to the left, and go down is acceleration is A prime. Go to the right, and then go to the right, and the inertial force is go to the left, making the ball like this. And in this case, this tension and mg, and the bob is stationary on the train, and it's like this. Is it okay? Everyone? Good? Now, so remember, conclusion. On the frame, not inertial frame, you have to count one force is the inertial force acting on the object. Inertial force is equal to the mass of the object multiplied by the acceleration of the frame and opposite direction. In the opposite direction. Very good. Now, we deal with this case, with our non-inertial frame. Whether we get the same results or not. So I use the frame of the ground, that is the inertial frame. I don't use the inertial force to see if I get the same answer or not. Okay? Agree? Another case. And then in this case, I will explain you why we have the initial force. So now, I consider the frame of the ground. Okay? The ball is I denote as the object 1. The train, object 2. The ground, object 3. Is it okay? So I consider the motion of the ball in the frame of 3 ground. That is the initial frame. So I don't have initial force. So the force acting on the object is mg and t. So I have mg plus t equal to ma, which a acceleration of the object with respect to 1 and 3, because I am considering the frame 3, so of course that is the acceleration of the object with respect to the ground. Agree? So then now you think about the relative motion. If we have A13 equal to A12 plus A23. So A12 is it what? Acceleration of the ball with respect to the train. Which value? On the train, how about you see the ball? Station. Right, so it is 0, okay? The ball is fixed. It's stationary on the train. If it's moving fast and then it's stationary forever. So, 0. So what is it? Acceleration of the train with respect to the ground. So, is it this one and this one? Alright? So this is A0, which I denote as before. Agree? So I plug this guy to here. So it's M A12 plus A0. A0 is the acceleration of the frame, inner train of the train. Agree? So from here I get mg plus t minus ma0 equal to equal to 0, but originally is ma12. So this means, what does it mean? What is the difference between this and this? The left hand side is the force, total force acting on the objects. The left hand side is the total force acting on the objects. In case of the inertial frame, you just have the normal force acting on the objects. Okay? And the right hand side is the mass and the acceleration in that frame. This is the frame of the ground. This is the frame of the train. In the frame of the train, additional with these two forces, you have this force. Okay? This force, and then the right hand side still MA. So here is the frame of the train, and this is non-inertial frame. And then the force here you set up is the inertial force. Okay? So if you look at the frame of the train, then additional to these two forces, you have inertial force. And the inertial force equal to minus m acceleration of the inertia. Okay? This is the reason. So the inertial force appear because you are considering some frame moving with some acceleration with respect to the ground. Otherwise, this force is zero. Agree? That is the originally of the inertial force. And of course, two cases. So far, Quang Binh and Quang already Bing use this method. And now I'm using this method. And then I see, okay, A2 plus A0. A2 is 0. So this line is equal to MA0. Is it the same results? If I go to the left, A0 go to the left, then my objects need to go to the left. Go to the right or go to the left, equal to MA0. A0 go to the left. T and mg need to go to the left. So I need some of this, get some vector go to the left. So the bulk need to be in this direction. So that T and mg having the some vector go to the left. Okay? So in this case, I have to go to this. And this one, I need T plus mg of A0 prime go to the right. So I have this case. So that T mg vector sum go to the right. Agreed? So both case is okay for me. I get the same results. And then for you, you choose whatever you want. Which method is okay for you? You can use the frame of the ground, or you can use the frame of the train. And then you need to get the same results in two cases. And you can use one of them. It doesn't matter. I already give you the maximum mark for both cases. Agreed? And now you understand what original of the inertial force, the appearance of the inertial force. And we can obviously prove by the relative motion. Because of the relative motion, it appears the new force. Okay? Break 10 minutes. We almost finished. Sorry. 10 minutes break and then continue. Now have some few minutes, 15 minutes, so we try to finish this one. Alright. So I introduced the third law of Newton. The third law of Newton have two objects. Okay? Object A and object B. And A act to the B some force. Instantaneously, the B react back A, the opposite force, with the same magnitude. You have FAB equal to minus FBA. And this, the third law of Newton. It's very simple. Okay? Next slide. I will introduce the force we meet every day. So the first gravitational force everyone know, and then we mentioned it from the beginning, right? That is the attractive force between the center of the Earth and mass, our mass. The second force is called the normal force or the normal reaction and the weight. So firstly is the weight. What is the weight? The weight of the body is the magnitude of the downward force it exerts on any object supporting. For example, the floor is supporting me, right? So the force I exert to the floor equal to the weight, my weight. And of course, I hit the floor some force. According to the third law of Newton, the floor will act me back the opposite direction to my body. And this force is called the normal contact force. So, example, I have a floor. So my body is here. So I hit the floor, the weight. Okay? The weight is act to the floor under my influence, and then under this reaction, according to the third law of Newton, the floor will act me back the normal reaction. It's called the normal reaction. And this force obey the third law of Newton. So the magnitude, they are the same. And this is the weight. The magnitude of the weight equal to the normal force. And they are pointing the same and the opposite direction. And the normal force putting on the object. And the weight putting on the floor which support the object. Okay? Relation between the mass and the weight. In this case, we analyze the force acting on the object having the mass m. So it has two force acting on the object is mg and the normal contact force, and it is at rest in equilibriums. Agree? So the second law of Newton says that n equal to mg equal to 0. Okay? mg and n, they're equal to 0. Remember, weight is a force acting on the floor, but not on the object. So you don't count it when you consider the force acting on the object. Agree? Only these two forces acting on the object. So for the magnitude n minus mg, if you project this vector along on y, then this is equal to 0. And then you have normal contact force equal to mg. And then normal contact force equal to the weight. So in this case, you have the weight equal to mg. So weight is the mass multiplied by g. Okay? In this case. How about other case? So weight equal to mg. Resting on the table. There are two cases. The first case is the table is horizontal. The table is horizontal. Okay, the weight equal to mg. Now, the second case, table is inclined. The table is like this. This is horizontal, the table. Incline to the horizontal some angle called theta. What happened? Okay? So in this case, the object is here. So you analyze the force acting on the object. Here is mg, vertically downward. Agree? And the normal contact force is perpendicular to the surface of the contact. The contact is here. So the normal contact force need to be perpendicular to this surface. So here is N. Agree? And I neglect the friction. Oh, there's some friction, okay. There's some friction, of course. There's some friction, okay. Alright? So in this case, I will have mg plus n and some friction, and then the object is at rest 0. Okay? I am assuming at rest. And now if I project this along OY, OX, OY, then you have mg along OY is what? Cosine minus mg cosine theta. Minus because this is pointing down and OY is pointing up. Alright? So n is plus n, friction is 0, so you get 0. So from here you give n equal to mg cosine theta. Comparing to this case, in this case, the weight equal to mg cosine theta is smaller than mg. So in this case, the weight is changed. It's not mass and mg anymore but multiplied by the cosine of the angle. Okay? So it's smaller. So when you weight, be careful to put the balance with the horizontal surface. Otherwise, you get the wrong answer. Smaller. Okay? So maybe you go to the supermarket, you take the table is up, and then they weigh the meat or something, and then you weigh less. Agree? You weigh less. Not even you have bigger meat. Okay? Alright. Another case. If the object having the mass resting on the floor and the floor is moving up and down like elevator, what happens? Okay? So in this case, you have elevator. Elevator is, for example, is moving up with the acceleration A. So you are resting on the floor of the elevator. So what is the force acting on this object? mg all the way. This is normal contact force and inertial force going down early. So you have n plus mg is 0. And then now you project on a y. Project on a y, what do you have? N minus inertial force minus mg equal to 0. So from here you have m equal to inertial force plus mg. What is the inertial force? Ma, magnitude, mg. So in this case it's greater than mg. So if you measure the weight when the elevator going up, so you feel heavier, right? Oh, 50 kilogram, and then the elevator going up, and then I measure my weight. What? 52 kilogram. I'm heavier, right? And the scenery is going down. Accelerator going down, then lose some weight. Lose weight. And then you will be lighter. Okay? So Z minus I. Minus I. Opposite direction. Agree? Okay. Friction. Friction we have just mentioned. Here we have static friction. Static friction is a friction appear when the object doesn't move. You have friction. For example, the case when the table is inclined, you have some friction to balance to the components of the gravitational force. But it doesn't move. Okay? That is a static friction. So the static friction is always opposite to the external force acting on the objects. Like the table is at rest, is weight balanced to the normal contact force. Now I push it, it's still at rest. I'm pushing, it's still at rest because it's appear the static friction to balance to the force of my pushing. Okay? So I push it or I pull it. It doesn't move because it's having static friction. Okay? So the static friction when no external force acting on that is 0. But when external force is balanced, static friction balanced to this force. So in case of the dynamic friction, when the object is moving, you still have the friction. And this case is moving with a constant velocity. For example, you have the friction is opposite direction to this, the direction of motion. And the simple case, we have the formula. The magnitude of the friction equal to the mu multiplied by normal contact force, where mu is the coefficient of the friction. The normal reaction of the surface is Rn. This is a formula to the kinetic friction. Okay? So, go home, you try to do this exercise and this exercise. This one, you take it later. I don't have time. So you do this exercise and this exercise. And we check together for the next time, next class. I will upload my slide to Moodle after I finish the class on Friday. Okay? Normally evening of Friday, I will upload on Moodle the list of exercise and also this. And you remember to do this exercise, we correct together this time. Okay? See you next week.